Yeah, thank you very much. And thank you very much for organizing this nice workshop. It's always a pleasure to come to Vilnius. So this talk is about frustrated optical lattices. I'm not going to talk anything about quasi-crystals, quasi-periodic systems, even though it's the Quasimodo conference, because I thought in this system we also have a very nice multi-component system that I want to talk about. This is work that we've been starting to doing 7-8 years ago, and it's now really coming into its own. And it's a very frustrating topic to work with for a very good reason. The reason is that we're now really going into the regime where you really want to do quantum simulations because we do not know what is supposed to happen. So I will not be able to, in most cases, give you a nice theoretical explanation and then show you curves that overlap and, oh, look, we exactly see what we expect. Because in many cases, we just do not know yet, or humanity doesn't know yet what's going on. So it's very interesting, but it means it's a lot of work for us because we have to double and triple check everything to make sure that we really do the right thing and don't have any kind of dirt effect that we just didn't think about. Okay, so it's an experimental talk. This is a picture of the experiment. The key players for the first part of the talk, the triangular lattice, was Mehdi Hassan, a postdoc at the time. He's now with Mike Tarbot in London at Imperial. And for the second part, the cargo-mill lattice, it's mostly Luca and Dan were the two PhD students. Luca's now a postdoc with us, who really were driving this forward. So as an experiment, moving an experiment is basically all of what we did last year. We moved the experiment just across the road into the new building because the physics department in Cambridge now recently moved out of the 1970s building that many of you might have seen into the nice, shiny new Wade Dolby Center. So we're very happy that we're in there, but moving an experiment is a lot of work. But now we're there, and now we can start to look at physics. And actually, we're going to look at very old physics with a new twist. So what we're going to talk about today is just the plain vanilla Bose-Hubbard Hamiltonian that you've all have seen, if you're old enough, more than 20 years ago already. So we're thinking about what happens if you have atoms in a lattice, a tight binding lattice. They're scalar, there's no gauge fields, no nothing in this case. So they just hop from one side to the next with hopping rate j, and they interact with an onset interaction u when they're on the same side. And then we all know, and Emmanuel showed us this 20-something years ago, that if j is much, much bigger than u, you're in the superfluid, so you're in the condensed phase. So you basically have a BEC where all of the particles sit at quasi-momentum 0. And if you then do time of flight of this, you see a sharp BEC peak here, and you see the satellite peaks at reciprocal lattice vectors because you're in a lattice. And of course, when you think about this one with a quantum gas microscope, you would see Parsonian number fluctuations on each lattice side. In the other regime, say you're at unit filling, you go to the regime where the repulsive interaction dominates, you get the Mott insulator, which you can really think of as a product of local Fock states. So you put one particle on each lattice side, and this state obviously minimizes the interaction energy because no particles ever meet. And those two limits, they're connected by a quantum phase transition, not a crossover, it's a phase transition, because this is a symmetry-broken state where the typical U1 symmetry of the superfluid is broken, while the Mott insulator is a normal state, there's no broken symmetry, and this phase transition happens at critical interaction strength of on the order of 30J in the 3D lattice. So this has been studied a lot in the last 20 years. We know for the standard case, say the square lattice or the cubic lattice, a lot on how this works, also how the dynamics goes, how critical scalings are. Most things are known. So how to get a new twist into this? How to do something different? Well, the answer is you go into a different type of lattice. A lot of the work that we see in cold atoms outside of the lattice is always saying kinetic energy is what it is, p squared, and we play with the interaction term. We add this interaction or that interaction, or we try to give it a new twist using topology. What we kind of can think of in the lattice physics is, well, we have this huge additional playground by playing with the kinetic energy, by just saying, how does the same system behave when it has a very different dispersion relation, by putting it on, say, a triangular lattice or the cargo-mill lattice. And the important point in both of those lattices is this motive of the triangle. Triangles give rise to geometric frustration, and the easiest way of seeing this is by thinking of the classical Ising model. The classical Ising model in the antiferromagnetic case, antiferromagnets are the most interesting case here. On a square lattice, you get a checkerboard pattern, up, down, up, down, up, down, and you can tie the plane with this. It's a nice arrangement. However, as soon as you have a triangle, you see what happens. You put, say, a down here and up here, and whatever you put here, one of those two bonds will be frustrated. And that's what geometric frustration is. Now, if you think of not Ising but Heisenberg, you realize that in a triangular lattice, by not having the planes in the z, the spins in the z direction, but in the xy direction, you can still make like a 120-degree order and still get like an antiferromagnet in the triangular case for Heisenberg. But for instance, in the cargo-mill lattice, you cannot. So the cargo-mill lattice is kind of the second step, which is even more frustrated than the triangular case. And now we can ask ourselves what happens here when we'll start with the triangular case. So if I just think of scalar bosons, I again have my normal Hubbard model, but because I have this different geometry, I now get a different dispersion relation. And of course, band structure calculations are easy. You can just do this numerically, and you get a band structure that looks like this. The Briand zone is a hexagon in the same way as it is, for instance, also in the Cargolay lattice or in the graphene lattice. In this case, it's a single band, which has a minimum here at the gamma point, and two maxima here at k and k prime. So in the normal case, which is kind of, if you want the ferromagnetic case where J is positive, that you normally have, well, this is a single minimum in the Briand zone, so your BEC will just form here, and don't care about much about the high energy degrees of freedom. So you expect the normal BEC at the gamma point. And you have two maxima at k and k prime, and those things are non-equivalent. They're two different points. They're not connected by a reciprocal lattice vector. This point and this point is the same because this is a reciprocal lattice vector, but this is not. In fact, you can also say that k is minus k prime, the time reversal partners, because they also live on opposite edges of the Briand zone. So if you now go to the fully frustrated case, where you flip the sign of the hopping, so to speak, then of course the band structure just flips around. And now suddenly you have two minima in the band structure. You have two degenerate but non-equivalent minima at the k and the k prime point. And then you ask yourself, what will the BEC now do in there? And that's where I claim this is in some sense maybe multi-component, so that I have a reason of being here, which is to say, well, in principle, your BEC could form at k, or at k prime, or a priori at any superposition of k and k prime. Now, when you think about the superposition, and everybody who has worked with spin-orbit coupling, like Ian has and many others, of course, and Gediminas, knows that this is not what's going to happen, because if you have a superposition of k and k prime, you have the superposition of two-plane waves, so to speak, which form a standing wave. So you get like a density wave, a density modulation. And if you have a repulsive interaction, then if you have a density modulation, that means you have points with higher and points with lower density, and that means that you in total have a higher interaction energy, because interaction energy goes like, if you think of Gross-Berezovsky, like n squared, so you have to pay extra for having these density modulations. So what you realize is that the system in a mean field regime will not want to do this. So what the system will want to do is, it will want to not be in a superposition, but either at k or at k prime. So we get like a new type of symmetry breaking in here. An Ising symmetry is that two symmetry is broken because the condensate, the ground state, will either be here or there. And like in the Ising transitions, it's a spontaneous symmetry breaking where it wants to choose the one or the other. And as I said before, k equals minus k prime. So this superfluid at either one of those two also breaks time reversal symmetry. So we call it a chiral superfluid. You can also think about this chiral. If you say at the k point, then you get like a little microscopic current along these plaquettes that goes, say, clockwise, and then at k prime, the microscopic current goes counterclockwise. So there's a sense of chirality of time reversal symmetry breaking in here. Okay. And the first people to look at this were not us by far. This was the group of Klaus Denkstock, already 15 years ago. What they did is they used like modulation techniques for key shaking. They were shaking the lattice, and by shaking the lattice, they could renormalize these hopping elements. So for them, J and J prime shaking in this direction or in the vertical direction, they could control separately, and they really gave us a very nice vocabulary of all of the phases and states that you can see there. So for instance, if they don't do any modulation, that both hoppings are ferromagnetic, so they're all positive, then you get a standard BEC at the K point, and the satellite peaks around it. Of particular interest for us is this case, what they call spiral 1, where all of the hoppings are antiferromagnetic. And then you see that the BEC peaks indeed show up at the edges of the first Briand zone, so populating the K and the K prime point. And they also could see this chiral symmetry breaking, because what you see there on the right-hand were averaged images. If they do this in a single realization, they sometimes get something where these peaks are more occupied, sometimes those peaks are more occupied. And if you look at what they call this chiral contrast, you really see the distribution that you would expect from a spontaneous symmetry breaking. So we could say case closed, nothing furthermore to see here, everything is all solved. Well, that's not exactly right, because what was done here is this was a lattice of tubes, so they did not have any lattice in the third direction. And that means this was very inherently a weakly interacting, weakly correlated system, so something that you really can describe by a classical XY model. They could see all of the phases in the classical XY model, but they could not go to something that's very quantum in nature. They could not go to a strongly correlated state because as you know, when you have Floquet states and you combine it with strong interaction, unless you do things exactly right, you can get a lot of heating. So here they were really like limited to this weakly interacting regime. So that's where we come in, and that's where we say, okay, how can we now go and look at, say, this chiral superfluid to mod insulator transition in this regime and combine this with strong correlations. Go into the regime where it's also very hard to simulate classically. And for this, I need to like remind you of one other thing that we did a long, long time ago, which is the story of negative temperatures. Classically speaking, you always just use 2 positive temperatures, and you know that if your temperature is very small, it means that most of the particles sit at very, very low energies, and if the temperature gets bigger, say your Maxwell-Boltzmann distribution gets broader, and you get more particles at higher and higher energies. And classically speaking, when you think about p squared, there is no upper limit to the energies here, so that's all that can happen. However, if you think of an isolated band in a lattice, or of a spin model, or of any other systems where the energy per degree of freedom has a natural upper limit, because you can just be at the upper edge of your band and no further, then you have the situation where you have a boundary also up here, and then putting infinite temperature in there just means that you get a flat distribution of all possible energy states. Perfectly valid, perfectly fine. And if you can do this, and if you have this upper limit, then you can also put a negative number, a negative temperature into the same equations, and you just get a distribution that's now exponentially increasing, where most of the particles will sit up here. And then finally, what the laser people call a totally inverted system, where everything sits up here at the highest energy states, that's now where you approach 0 temperature from below. This is all perfectly fine. This is all perfectly standard thermodynamics. Negative temperatures are as stable and as nice and as good as positive temperatures. It's like matter and antimatter. They're both perfectly stable on their own, but you better don't match them, don't mix them. And you need to have a system where you have this upper limit in kinetic energies, which a lattice naturally provides for us. So why am I telling you this? I'm telling you this because of this very, very deep and very, very trivial relation. If you're asking about the thermal states that you can have, where they're given as over the exponential of minus the Hamiltonian operator over kVt. And very obviously, if you put a minus sign here, you go to minus the Hamiltonian, and you go to minus the temperature, the minus signs cancel, and you get the same state again. So any state that you have at positive temperature for a Hamiltonian has the equivalent state at negative temperature for minus the Hamiltonian, just because the 2 minus signs cancel. And this was a statement about thermal states, but because the statement is also true for all eigenstates when you talk about energies instead of temperatures, and you can think of the dynamics in terms of the eigenstate dynamics, it's true for the full quantum dynamics, for anything that you want to do. These 2 things are really equivalent. You can just go back and forth by putting in 2 minus signs. Now, in the Hubbard Hamiltonian, you of course have 2 parameters. You have J and U. J is the one that we would love to like change the direction of, change the sign of to really go to this fully frustrated system, but we want to do it without any shaking, without doing actively anything to the lattice. And U is something that we use potassium-39, that we can control with a Feshbach resonance. We can go from repulsive to attractive, which means we cannot just flip the right signs and get what we want. So what we want is we want to study the fully frustrated model, J negative, at repulsive interactions, the standard case, and at positive temperatures, the standard case. And this, due to this very deep and very trivial relation, is exactly the same as the phase diagram of the unfrustrated model, which is good because that's the one that we happen to have in the lab and it's stable, at attractive interactions, which you can get to with the Feshbach resonance, and a negative absolute temperature. So the only question left to ask is how do you get to these negative temperatures? Because you can't just heat the system. Well, second law of thermodynamics tells you that it goes all the way up to infinite temperature, but that's the state of maximum entropy. Heating above that into negative temperatures means reducing the entropy again, so you can't do this via heating. You have to find a different trick. And the trick for us is to use a bridge, and the bridge for us is the deep mod insulator. When you think of the mod insulator in the atomic limit, where you can really neglect tunneling, the n=1 mod insulator, as I said before, is just a product of Fock states, 1 particle on each lattice side. You think of your Hamiltonian, and that's obviously the ground state for the repulsive case, because repulsive interaction is the only energy scale that you have, and it's really 0 in this case because particles never meet, so it's obviously the ground state. By the same logic, if you go to attractive interaction, the same state, the same wave function is the highest excited state, because whenever particles meet, they get an attractive negative energy, which means it would lower their energy. So when you never have this negative energies, they're at the top end of the spectrum. So it's an eigenstate for both positive and negative temperatures, And it basically means that if we now stay here, have this state, and now we suddenly flip from Hamiltonian to minus Hamiltonian, we flip the scale around and we go from here to here, ideally without any heating. It's a discrete operation, it's a discrete flip, going from H to minus H, but it should ideally not heat the system at all. So this is then the measurement protocol that we want to do. We start with a normal superfluid, generate a normal repulsive Mott insulator, and then we can do either of two things. The first thing is our control experiment. We do nothing, we just stay in this Mott insulator, ramp down the lattice again, and look at the phase transition from the Mott insulator back to the superfluid. Or, when we are in this deep Mott insulator, we use the Feshbach resonance to flip from repulsive to attractive interaction, which naturally means we also go from positive to negative temperatures, and then we study the phase transition in this case, when we decrease the lattice and go down into the superfluid. Everybody with me so far? Good. Then here is the results. What you see here is now the control experiment at positive temperatures. We start off in a deep lattice. So we start off with this Mott insulator, which in time of flight, because the particles are localized, is a big featureless Gaussian blob. And then we decrease the lattice, and we go back from the Mott insulator into our nice superfluid state. If we do the same thing with a slightly bigger interaction, so instead of 50 A0 scattering length, we go to 150 or 250, the same physics happens, but because U is proportional to A, it now means we have to go lower in lattice depth to go through the same transition. All as you would expect. And now, if you do the same thing on the attractively interacting case at negative temperatures, you see the same thing or a similar thing. You also see that you start off with your Mott insulator here. There's not much difference between these distributions. And then you see that we now start to really see this occupation at the corners of the Briand zone, as you would expect from this chiral superfluid. But that's maybe not yet good enough to claim, oh yeah, we now have this chiral superfluid. We should try to be a bit more quantitative, and that's then where all of the nastinesses come in. Because first thing we can do is we can say, okay, well, where is the critical point? We can measure it experimentally, and we say the critical point on the positive temperature side is on the order of U/J 25. This agrees with quantum Monte Carlo, and it's as you would expect. On the attractive side here, however, quantum Monte Carlo is not possible because it's a frustrated system. Even for bosonic QMC, you run into the sign problem. So this makes this frustrated system a very hard problem, where it's very hard to really calculate the ground states. We do not really know the phase diagram because of the problem that we can't use quantum Monte Carlo. So what we can do is we can say, okay, let's do mean field, which of course is very bad, but then try to do cluster mean field, where instead first you do normal mean field, then you do mean field on the level of a small cluster, let these clusters go a bit bigger. That's kind of how big you can go, and then you extrapolate to infinite cluster size. If you extrapolate in cluster mean field, your phase transition should happen around here, and you can see that this basically nicely agrees with what you get in the experiment. A nice conversation to coffee about is what is these data points. That's where we use machine learning to try to learn the phase transition from the experimental data. Upshot is it basically works, but it does not give you anything new because you really have to make so many choices on how you set up your machine learning that you can get this result, but also a different result if you want to. So for some cases, machine learning is great. For other cases, not so much. But that's a discussion for coffee. So the key thing to see here is that the frustration really reduces the critical U/J by a factor of 3, which is what you would expect because you cannot now really satisfy all bonds at the same time. The ordered state that really minimizes the kinetic energy will be less stable, more susceptible to interactions and other effects than it should be in the unfrustrated case. The same story that you get with antiferromagnets. When you look at an antiferromagnet in a frustrated system, you typically get a big reduction in the antiferromagnetic Daniell temperature or even the absence of antiferromagnetism that gives then rise to spin liquids in the ground state. So the same story happens here. We are far more susceptible to interactions than we would be without the frustration. Now we can go to open questions and ask ourselves, well, how does the phase diagram really, really look? Because this chiral superfluid breaks two symmetries, right? It breaks this U1 symmetry and this additional Z2 symmetry. This gives different possibilities. First question is, do we have a direct transition from the Mott to this chiral superfluid, or do we have an intervening phase, which would be a chiral Mott insulator, where the chirality is already broken, but it's still a Mott insulator, not yet a superfluid? And obviously, this is a question that people have asked also a long time ago. One of the first ones was Ehud Altman and his team in 2014. And they looked at the mean field phase diagram of this one in 2 dimensions, and they saw that, well, they see a direct transition from mod to chiral superfluid, but if they also introduce small nearest neighbor interactions, then they start to get this chiral mod insulator. That makes them suspicious, and they're saying, well, we know that ordered phases are overestimated at the mean field level, so maybe the intervening phase should be there. They give arguments why it might be there, but they couldn't conclude anything. Andreas Leuchli, a few years later, and the Danchita group even later, they tried to look at this with heavy numerics, doing DMRG on like small cylinders, making them bigger and bigger and bigger, and asking what is the answer that they got. And when you read the abstract of Andreas's paper, it's very, very technical, and it says we see certain modes which are in agreement what you would expect in this case. We also see other signatures that are in agreement with what you would see in that case, and they can't conclude anything. So what I would say is the existence of this chiral mod insulator is an open question. And again, that basically comes from the point that this is a very hard many-body problem for us because we can't do quantum Monte Carlo because it's a frustrated system. So even scalar bosons can be hard. Okay, and now from the experimental point of view, well, maybe there is this very small sliver of chiral mod insulator, but it's certainly not a big range. So seeing this in the experiment would be very, very hard. But we still care about it because it gives us a lot of insight in what the superfluid transition could be. Because if there would be an intervening chiral mod insulator, you would have a sequence of 2 transitions. That would mean you would have a sequence of 2 continuous phase transitions. However, if it would happen at the same time, it could very well be a discontinuous first-order phase transition, which would have a very different critical behavior. So we're kind of thinking that maybe we can go in there and can try to see this on the experiment. And of course, we can't really predict this order theoretically because we can't even clarify whether we have this chiral phase in between or not on the numerical side. So let's go in and try to ask ourselves, well, before we go in there, we can of course ask, if you can't do anything quantum, what does classical physics tell us? And there have been a lot of classical Monte Carlo on the classical XY model. So the first one is a fully frustrated 2D XY model on a square lattice, but still fully frustrated. They indeed see 2 transitions where they see the Ising ordering temperature is slightly above the BKT. So it's the sequential model, but they're very, very close. And then they're saying, well, but this is maybe also the wrong model because what you will have is, due to the mean field interaction, you will have like this kind of coupling between the 2 ordered fields at K and K prime. So maybe a better way to include this into classical numerics is by saying, let's go to coupled phi to the 4 theories to really model these critical modes. And if they do this, then they start to see the Vicari group in classical Monte Carlo saw that it might merge into a first-order phase transition. The group of Ludwig Mattei did something akin to what they did in the experiment in Hamburg. They were asking, okay, if you do this in the BEC case, and you look at the standard BEC transition, which means you do this in a 2D array of tubes, that the system is kinematically 3-dimensional, and you really can do standard condensation, they also see a discontinuous transition into this chiral superfluid state. But because this is, again, a different system, what really happens in the 2D case, when you go from strong to weak interactions, is an open question. So we try to get there experimentally, and also there it turns out to be a very, very hard question. So the first thing you do is you just say, okay, let's look at the emergence of coherence when you ramp from the mod insulator to the superfluid in various amounts of time. The pictures that you get is if you do this very quickly, look first at, say, the positive temperature case, you see this very big plobs here, but you already see the structure of what will be the superfluid at long times. So you start to see, okay, there's a continuous phase transition where the peaks just get sharper, 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 meaning longer, longer, longer range coherences as you ramp slower and slower. And you start, if you don't look too carefully, see the same thing on the attractive side. So if you do the standard analysis that experimentalists do, you look at the visibility, do a log-log plot. In both cases, you would see, okay, I get a power law approach to a state with high visibility. And then you're asking yourself, okay, what is this indicative of? Well, it's indicative of a continuous phase transition, but then the very suspicious point is that you get to see different power laws. If it in both cases would be a standard BKT transition, you would expect maybe the same power laws here. But then again, when you also think carefully, you realize that, well, actually, because when you look at the visibility, it just tells you you have these peaks, but it does not tell you really how sharp these peaks are. So it just tells you that the approach to the phase transition is smooth, but not yet about something in the critical regime really, really close to the phase transition. Another experimentally puzzling fact for us was that this is a single shot. And we always see K and K prime almost perfectly the same occupations. Now, because these are 2D systems, we have a whole stack of them. It could just be the averaging over the different stacks, but we think it's more, because the averaging over the stacks, it's not so many of those layers. It should still give rise to higher fluctuations. So there must be something with small domains, we believe, even within the 2D planes. So we can try to go further. We can try to say, okay, if you do very careful, longish time of flights, in this case 12 milliseconds, this is potassium, so 12 milliseconds is quite some time. And then you're asking yourself, really, how sharp do the peaks become as a function of this evolution time, as a function of the emergence of coherence times? In theory, of course, a superfluid has long-range order, so momentum space, it should become a delta peak. But in practice, for any finite time of flight, of course, no peak can be sharper than the width of the original cloud in situ. And that's what you can see here in the inset. This is like simulated data. This is how broad the peak after time of flight would be as a function of the coherence length. If you only have one or two side coherences, you see a broad peak, like we saw in the previous slide also experimentally. It's big, blobbish, and then it becomes sharper and sharper and sharper as the coherence length gets longer. But you can also see here that the lines at 16 and infinity, they are already very, very close to each other, because at this point then, the cloud size you see is really dominated by the in situ cloud size. And now if you look at the experimental data for the positive temperature case, the unfrustrated case, coherence length extracted as a function of the ramp down duration, we see something that comes up like this, and then up here it seems to diverge and becomes compatible with infinite range correlations, as you would expect in a superfluid, but we kind of gray these curves out a little bit because they're saying something quantitative. 50 looks almost the same as infinity, so we don't have very much discriminatory power up there. Another thing that we see that is surprising, maybe at first glance, is that we also see some kind of breathing mode oscillations on top of here. And this we believe, and we've seen this previously in 1D simulations, is an artifact of the harmonic trap, that while the system changes character, it's not just a homogeneous system, it's really also undergoing some kind of breathing type oscillations. So nonetheless, if you like take the eyes of love and you try to fit a power law through this, the power law that you get out is probably somewhere between 0.4 and 0.6. And 0.4 would be the prediction for the standard BKT transition. And we've seen previously also in the square lattice case that we sometimes see higher power laws on the order of 0.5, 0.6. So this is exactly what you would expect experimentally for like the normal mod to superfluid transition. So all as expected. Now, it's compatible to what you see in the square lattice. And also, it should be the same because really the low energy physics in an unfrustrated case doesn't care about what happens at the high frequencies, at the high energies. Now, if you go to the to the attractive case, the negative temperature case, the fully frustrated case, you see something that looks different. You see that now you have far less of these breathing mode oscillations, which maybe is a good thing. You also see that your coherence length grows much, much, much slower. This is an exponent of 0.32, far below 0.4. And you also see that, well, the coherence lengths that we get, they never really grow about, say, 3 lattice sites. That's clearly a different behavior. And now the frustrating part for us is, of course, in the time scales that we can have, and this is now really going up to like hundreds of milliseconds, is that it could still be a slow oscillation that continues, but this is just like the next underswing of this breathing mode, and it comes up here like this. Or it could be that it's now really saturating here at this point. So when you think about the possibilities, one possibility that it could be is that it could be something where you really have 2 transitions. So you first have the easing transition, then followed by the standard BKT transition. And in that case, of course, the easing transition turns out to have a critical exponent of 0.32. So it could be that we just see the easing transition, and then, of course, the BKT transition would be faster, but the BKT coherence length cannot grow above the size of the initially formed easing domains, so therefore we see the smaller of the 2 power laws. It could also be that we have a single continuous phase transition with a new critical exponent that's different from either easing or BKT. Or it could be that we have a weakly first order phase transition, which means that on the mod insulator, there's no chiral mod insulator, on the mod insulator side in this case, the coherence length would stop growing at 4. That's kind of the critical value. And then there would be the jump to the infinitely correlated system. And we don't see this jump because we're now really trapped in this metastable mod state at coherence length 4. And this really is a quantum simulation of an unknown phase transition. And there should be a picture on the other side. This is not how the slides look on my computer, but okay, let's see what happens. So what this really means is that we are now really doing a quantum simulation of a so far unknown phase transition. And I think we now know also what the next steps are, how to get to like even longer times, and how to like reduce the effect of the initial cloud size further. So hopefully in the next 6 months we can get to a final answer of what the story is going to be. And there would be more stuff to happen on the cargo mail lattice, but I believe I should stop here at this point, and thank you for your attention.
So, thank you. Questions? Maybe one question just.
What is the interplay between geometry, 2D, 1D versus these transitions? Because in the paper by Altman, they do some DMRG analysis in ladders, whereas the mean field prediction is for a 2D full lattice. So can this intermediate phase be just an effect of finite confinement in one direction?
I mean, that is possible that you say, okay, if you have these kind of ladders, you could have an intervening carrier mod insulator on the ladders that would go away in the 2D limit. That's exactly the thing that we don't know, right? That's exactly the question.
Okay, so let us thank the speaker once again.